In this video, we're going to take a look at directional derivatives. So first, let's define what a directional derivative is. So we're going to talk about the directional derivative of a function f in a certain direction given by vector u. And the way we're going to write that directional derivative, we're going to write capital D, we're going to write subscript describing the direction vector u, and then we write the name of our function. So let's draw a picture and understand geometrically what this directional derivative is. So suppose we had a surface. Let's say we're in three-dimensional space here. We've got a surface given by z equal f of xy. So let's say, just for the sake of our picture, maybe our surface looks a little something like that. And then we're going to specify a direction. So let's say vector u looks like that. Could be a direction in the xy plane, whereas we'll see some other examples where it could be a direction in space as well, depending on the context. But let's just say here it's a direction in the xy plane. So what we're going to do is we're going to slice through our surface parallel to vector u. So let's imagine taking a plane parallel to u, maybe something like that, just for the sake of our picture, and we're going to slice through our surface. So anytime a plane slices through a surface, that's going to create some curve. And if we just zoom in on that curve, let's say that curve looks something like that, then at any point along that curve, we can look at the slope of the tangent line. And the slope of the tangent line is what this d sub u of f, in other words, the directional derivative of f in the direction u, that's what is being represented there. So directional derivative giving you the slope of the tangent line, and in order to calculate that, you need to know your function and you need to know what direction you're interested in. Here's the formula for the directional derivative. D sub u of f is equal to the gradient of f dotted with u. We talked about the gradient in the previous video. And what's really important here is that this vector u that's specified in the direction must be a unit vector. So meaning vector u must be 1 unit long. If you're talking about a direction in terms of a vector that's not a unit vector, you need to scale that vector down so that it's 1 unit long. The reason why we have to do that is because if our vector u had any length other than 1, let's say vector u had length k, then when we calculate the gradient dotted with u, we would get k times the slope of the tangent line. So in other words, if vector u is not a unit vector, then our answer would be distorted. And in order for this to be geometrically meaningful and to give us the slope of the tangent line, then we really need vector u to be 1 unit long. Here's our first example where we're going to practice the directional derivative. So let's say that we've got a function which involves x and y, and this measures temperature. Temperature will be measured in degrees Celsius, and x and y are our position. They're going to be measured in kilometers. So this could be something like maybe a city built on very flat ground. So we've got this region of the xy plane that we care about, and we're interested in measuring temperature at all these different points in the city. For example, that could be our context. So the idea is that we're going to start off at the point xy equal 4, 5, and we're going to head towards the point 2, negative 2. So we have a sense of what direction we're going in. And we want to figure out the initial rate of change of f. So that means at the moment that we're leaving the point 4, 5 and heading towards 2, negative 2, what is the rate of change of f at that moment? So that's an instantaneous rate of change that we're calculating. All right, well, first thing we'll do, let's figure out our direction. So when you're thinking about direction, think about the endpoint minus the starting point coordinates. So for the x coordinates, 2 minus 4, and for the y coordinates, negative 2 minus 5. That gives us a vector representing our direction, so that would be negative 2, negative 7. Okay, so that's the direction we're heading in as we start off at 4, 5 and head towards 2, negative 2. Now we know for directional derivatives that we need a unit vector. So we're going to create a vector u that is just a normalized version of this, meaning we're going to scale this vector down and make it 1 unit long. And the way we're going to do that is we're just going to calculate the length of this vector and divide by whatever that length is. So vector u is going to be our vector -2, -7 divided by its length. In other words, if u were, say, 3 units long, you just, if your direction vector were 3 units long, you would just divide that by 3 to create your unit vector. So to get your vector u, take your direction vector, divide by its length. All right, so the length of this vector, we're just going to square the components, sum those up, and square root that. That's root 53 from linear algebra. That's how we calculate the length of our vector. So 1 over root 53, and then that's times our direction. So we now have a nice unit vector encoding that direction. Okay, next thing we need is the gradient of f. So f involves variables x and y. That means the gradient of f is going to have 2 components. We'll take our partial with respect to x. That's going to be -9 minus 2y, and then partial of f with respect to y, -6 minus 2x. Okay, now we actually need to evaluate this gradient at whatever our starting point is. And we can see from the question, the point that we are starting at, 4, 5. So those are the values that we want to sub into the gradient, and you can just write something like gradient of f at 4, 5 if you want to show that you're evaluating. Okay, so let's plug in. The y value is 5, so that first component is going to be -19. The x value is 4, so we're going to have -14 for our second component. Okay, so now we know numerically what our unit vector looks like, and we know exactly what our gradient looks like at our starting point. So we're ready to calculate our directional derivative. So d sub u of f, we're going to take our gradient, dot it with our unit vector, and then we'll have a numerical answer. So -19 minus 14 dotted with the 1 over root 53, -2, -7. The square root can just go out in front. So 1 over root 53, and then we'll perform our dot product. So we're going -19 times -2 plus -14 times -7. That gives us 136, so I'm just going to write that number on top. So 136 over root 53. You could rationalize that if you want. I tend to just leave it like that. And then let's talk about units. So the units are going to be the units of f divided by the units of the square root of x squared plus y squared. Or if you were doing another version of this problem where your function actually involved x, y, and z, you could see a situation where you had units of the square root of x squared plus y squared plus z squared. So that's not the situation that we're in, but if your function did have 3 variables, that's what that would look like. So I just really say that as an aside. In this case, f is a function of 2 variables, so we're talking units of the square root of x squared plus y squared. Typically in this sort of problem, x and y will have the same units. So in the denominator, you're really just thinking of what are the units of x or what are the units of y, if those units are the same. So in this case, our function was measured in degrees Celsius, and x and y both were measured in kilometers. So we're talking degrees Celsius per kilometer. So at the moment that we leave that 0.45 and we head towards 2, -2, the rate of change of f at that moment, 136 over root 53 degrees Celsius per kilometer. So a train travels as above at 2 kilometers per minute. What is the initial rate of change of f experienced by the train? All right, well, we know from above that our rate of change of f with respect to distance was what we calculated in part A. So I'll write this symbolically first. Let's say we want to find df by dt. We want to figure out how fast is f changing with respect to time. And what we did in part A, we found rate of change of f with respect to distance. So let's use s for distance. If we then want to complete this, we need to multiply by ds by dt. So this is the rate of change of distance with respect to time, otherwise known as speed. Okay, so if we just take our 136 over root 53 degrees Celsius per kilometer, and we now multiply that by the train speed, which is 2 kilometers per minute, then sure enough, kilometers will cancel out nicely, and we'll have our rate of change of f with respect to time. So we'd have 272 over root 53, and now that's degrees Celsius per minute. All right, so at the moment that this train leaves the point 45, heads towards 2, -2, it's getting hotter pretty quickly. So that's how we use directional derivatives. Thanks for watching.